start in chapter 5 talking about rational functions. So everything we were doing in chapter 4 was polynomials. We talked about, finding the zeros, finding x and y intercepts, drawing the graphs of those things. We're going to do all the same things now, but with a rational function. And when I say rational function, it has the word ratio in it. I'm just talking about fractions. So a rational function is just when you divide two polynomials. We've been looking at individual polynomials. Now we're going to be dividing two polynomials and looking at those. The first piece that we need to look at with these is the domain. When we were talking about polynomials, our domain was always everything. The graph kept going in both directions. When we're talking about these rationals, though, we have to worry about something. Because of the fraction, what can't happen in a fraction? Well, we don't leave a square root there. It could be there at some point, but we never leave it there. And what else? What's the one thing that's like impossible? If you type it in your calculator, it tells you error. Right. You can't have a zero on the bottom. So when I'm talking about the domain of these, we're really worried about what makes the bottom zero, and x can't equal those numbers. Those are going to be the places where our graph does funny things. So we will be talking a lot about those moving forward, and that's our first piece today, is taking functions and finding their domains. So here we go. When I am finding these domains, I do not care about the numerator at all. All I'm concerned with is the denominator. I know that if it's a fraction, the denominator cannot be 0. So that tells me my x cannot be -5. So for my domain, how would we write that using integral notation? Good. I'm going to stand by what I've done in the past. If it's just one number, x can't equal, I do want you to go ahead and write that. If it's more than one, and you just told me that x cannot equal, then I would accept that as well. Okay. B. So I know in looking at this, my denominator cannot equal 0. So x squared cannot equal 4, then what would you do? If you add a square root, you mean? So x cannot equal plus and minus 2. So since it's more than one value, you could leave it like that. In integral notation, it would be -infinity to -2, union -2 to +2, union 2 to infinity. It gets a little bit long, which is why in those cases, if it's more than one, I have let you just say x cannot be those things. So far, so good? C. So it's a fraction, the denominator x squared plus 1 cannot equal 0. If I subtract over my 1, x squared cannot be -1. Square root plus and minus, you get x cannot equal what?
Plus or minus I rather than 1.
Yeah, and the square root of 1 is 1, so you could just say plus and minus I. Okay. In terms of graphing that, can we graph I? No. So does that really impact my domain if it's imaginary? So what do you think our domain is? Right. If it's just an imaginary number that it can't equal, then our domain is still -infinity to +infinity. Okay. D. My common denominator is 3. Can 3 ever equal 0? So what's your domain? Yep. Negative infinity. You don't even have to go to 3 because you can plug a 3 in for x, you still don't get 0 on the bottom, so it can be anything. Negative infinity to positive infinity. Alright, you guys do E for me. So what can x not equal? So how do you write that? And why do we have to use parentheses on the 1, not brackets? Good. Remember, not equals, always get parentheses. Okay. Are we all right with the domain piece? Now, I want to show you something. Here are two functions. This one's written as a fraction, that one is not. Over here, if I tried to simplify this, what can you do with x squared minus 1? How can you break that down? X plus 1, x minus 1, difference of squares. And what happens now?
It's just x plus 1.
Mm-hmm. But these two things are actually, if you look at their graphs, they are not identical for one reason. What's the domain of this one? There's no fraction. Its domain is negative infinity to positive infinity. Over here, if I look at the original, what's my domain? Negative infinity to 1, union 1 to infinity. When you're talking about domains, even if things cancel out, your domain is based on the original. So even though these things reduce to the same thing, they are not equivalent because they have different domains. Your graphing calculator isn't necessarily going to show you that because it does reduce things before it graphs. But they're actually different in that if you look at the graphs, the second one is just a solid line. The first one would actually have an open circle on the line when x is 1 because you couldn't plug a 1 into the original equation. So the graphs look almost identical, except this one will have an open circle in it and the second one won't. And that's something we'll talk about more later. But I just want to stress the importance when you're looking at domain, look at the originals, not what it reduces to. It's always based off the original problem. Okay. In graphing rational functions, we are going to have asymptotes in our graphs. Asymptotes are lines that our graph is approaching without actually touching. There are three types, horizontal, vertical, and oblique, that we're going to look at. It is possible that a graph may at some point cross over a horizontal or oblique line, but it will never touch a vertical asymptote because those vertical asymptotes have to do with our domains. So to start us off, we're going to graph a couple common rational functions, talk about their graphs, and look at where these asymptotes occur on those graphs. So I want to look at the reciprocal function first, 1 over x. Domain, you could probably tell me that just by looking at it. My domain, what's the one thing x can't equal in this problem? 0. So my domain would be negative infinity to 0, union 0 to infinity. But the range really isn't so obvious just by looking at the equation. So let's see if we can draw a graph and get the range from that. Let's plug in some numbers. If I plug in a 1, 1 over 1 is 1. If I put in 2, 1 over 2, 1 half. If I put in a 3, 1 over 3, 1/3. Okay, what if I put in a fraction? What's 1 divided by 1 half? What is it? 2. So if I put in a 1 half, I actually get out 2. If I put in a 1/3, I'm actually going to get out 3. Can I plug in 0? No. So what we're seeing is this is getting closer to my axis, but we know it can't equal. No matter what I plug in for my x, will 1 divided by something ever turn into 0? No, I'm still going to be getting these positive answers. It's just approaching the x-axis. Okay, let's do some negatives. If we put in -1, we get out 1 divided by -1 is -1. 1 divided by -2, -1 half. 1 divided by -3, -1/3. If I put in a -1 half, we get out -2. -1/3 gives me -3. So we're getting the same type of graph, just negative this time. Okay, so now can we look at this and give the range? This is coming from the negative, so it's -infinity to, did it ever hit 0? Union, and then we hit everything above 0. So it's -infinity to 0, union 0 to infinity. Okay, some questions that we haven't answered about our graphs in a while. Increasing, decreasing, and constant. Okay, so as I'm going from left to right, what's this section of my graph doing?
Decreasing.
Decreasing. You list the x values, so that's coming from -infinity and stopping when x gets to 0. What's this section doing? It's also decreasing, so union 0 to infinity. So there is no increasing in this graph. Since we have to go from left to right, it's always falling. Discontinuity. That's saying where is there a break in our graph? At what x value? So that's the only place our graph has a break. Vertical asymptotes. That means what vertical line is this graph getting close to, but not actually touching. The thing about asymptotes, since they're lines, I want you to write them as equations. A vertical line is x equals, so it's at x equals 0. Horizontal asymptote is the same thing except horizontal. The equation of a horizontal line is y equals 0. When we draw these, you will typically draw them in as just dashed lines. It's kind of hard when it's the x and y axis, you can't really see the dashed line. But if it were somewhere different, we would draw them like that. Okay. Something else we haven't talked about in a while. Even and odd. Remember, even means symmetric to the y-axis. If I flip this graph over the y-axis, does it overlap itself? No. So it's not even. Odd means symmetric to the origin. So you would have to flip this graph twice, over the x-axis and the y-axis. If I do that, does it overlap itself? If you flip over, that piece come here and then flip again, goes down and overlaps. So this one is So trying to review some of those terms we haven't talked about a little bit.
Okay, so even if you just flip it over y,
Mhm.
the other you have to flip it twice.
Yes, X and Y.
Okay. Does it matter which one you do first?
No. Other questions? Let's graph some of these. I think I do want to change this problem if this is okay with you. I want to make this negative 1 over x plus 4. I want to look at something slightly different there. Okay. So let's talk about the graph. We could use transformations. What will the plus 4 do? And what's the negative do? Flip over the, like making your y's negative, so it flips over the x. Okay. Parent functions get a little bit ugly to graph on these just because we're going to have so much stuff. So you want to just very lightly sketch your parent function here. My parent function is just 1 over x. So we know 1 over 1 is 1. 1 over 2 is a half. If I put in a half, I would get out 2. And same thing with your negatives. So I'm just going to do a really rough sketch here. So this is what our original 1 over x looks like. Now, if you flip this over the x, what's going to happen? What does it look like if you flip over the x? Yeah. This one's going to be here, and that one's going to be down there. Just going to put them in the opposite places. When you move up 4, we're not only moving our graph, we also have to move our asymptotes. This one has a vertical asymptote at 0. If you move up and down, does that change your vertical? No, but it has a horizontal one at 0. So it's now going to be at 4. So I'm going to go ahead and draw that in first. So my horizontal asymptote, we draw that just as a dashed line. That will be at 4. The vertical asymptote will stay at 0. So if I flip this, my point -1, -1 would come up to 1, 1. And then we go up 4. And -1/2, -2. We'll go to -1/2, +2, and I flip it. And then we're going up 4. Over here, if I flip this one, it goes to 1, -1, up 4. Flip those and up 4. So my graph looks like this. The main thing that I'm wanting to do on these, the graph itself, I want you to have a rough idea. I'm not going to be as much of a stickler about, the 3 exact points. What I'm really watching is, do you know what happens to your asymptotes here? So the domain of this graph, did that change at all? No, it's still -infinity to 0, union 0 to infinity. My range. What's the range of this graph? Negative infinity to, where do we have a break that we never have? Negative infinity to 4, union 4 to infinity. So moving our graph up and down is going to change our range on these. The asymptotes, so I typically just say VA for vertical asymptote. It's a vertical line, so you have to give me the full equation. Vertical is x equals, where's my vertical asymptote at? X equals 0. Horizontal asymptote, we call that HA. So the horizontal line we don't touch is y equals 4. Asymptotes are lines, so you have to give me an equation on those. Questions there? Let's look at the notes. So we're going to have the same parent function this time, right? I'm just going to very lightly sketch that in. Again, that's not my main concern there, but I'm thinking about 1 over x. If you guys want to just put your nice points, 1, 1, if you know what it's going to look like from there, I'm okay with that. If you really only have those 2 exact points in this scenario, that's okay. So if you want to do 1, 1 and negative 1, 1 and then just sketch in. That's my parent function. Okay. Let's think about our transformation. If I add 1 to my x, what will that do to my graph? If we add to x, it goes to the left. Okay. So what's going to change? If I move left and right, does that change my horizontal asymptote? No, but moving left or right, that would move my vertical. It was at 0, so if I go left, it's now at negative 1. Or you can tell your vertical asymptote is just the number you can't have in the denominator. You can't plug in a negative 1. Okay, and that's all we're doing. So then if I move my point left 1 and sketch in my curve, my horizontal didn't move. This left 1. Yes.
Okay, so your blue line down, you do left 1 also, like it's something different.
Yes.
And you start at 0 all the time.
Yes, because the parent function was at 0 there.
When I do my graph, it goes through it goes through 0 too. So if I move over 1,
That's okay because
oh, so then
now it's negative 1. Alright. So my domain. You can get it from the graph or the original equation. If we look at our equation, the one thing x can't be is negative 1. If I look at my graph, it goes from negative infinity to this vertical asymptote is the value I don't hit, which is negative 1, union 1 to infinity. My range from negative infinity to, where's my breaking point here? 0. That didn't change. Vertical asymptote. What is the vertical line that we do not touch? Horizontal asymptote. The horizontal line we don't touch. questions on that? I want to look at a second common function today. It's called the reciprocal square function. So it's 1 over x squared instead of 1 over x. The domain, we could graph it and give the domain, or you could look at the equation. What's the one thing it can't hit? What's the one number you can't plug in for x? Okay, let's graph this. If I put in a 1, 1 over 1 squared is 1. If I put in a 2, I get 1 over 4. If I put in a 1/2, it actually gives me out 4. So this piece looks similar, it's just a little bit steeper because of the square. What's going to happen if I plug in a -1? Well, -1 squared is 1, and 1 over 1 is 1. I'm getting the same thing. If I put in -2, I get 1 over 4, so 1/4. I get the exact same points out because the square takes away the negative. So this one still has a horizontal asymptote at 0 and a vertical asymptote at 0, but we're never hitting the negatives. So what's my range here? My graph starts at 0, we don't hit it, so it gets a parenthesis, and it goes up forever, so it goes to infinity. As I go from left to right, this section of the graph is increasing, so from -infinity to 0. From 0 to infinity, it is decreasing. Where is this graph discontinuous? And x equals 0 again. That's where we have the break in our graph. Vertical asymptote is x equals 0. Horizontal asymptote is this graph even or odd? Even. If you flip it over the y-axis, it does overlap itself, so this is an even function. Sound right? I want to do one more graph. Before we graph this, I want to kind of test you on something. Some of the homework questions tonight, they're going to give you an equation like this, and they're going to say what are the vertical and horizontal asymptotes. Do you guys, can you look at that and tell me what those would be without drawing the full graph? Your vertical is what makes the bottom 0. So that would be at 2. Or if you think your vertical asymptote starts at 0, the -2 would move it to the right 2, so it ends at 2. So our vertical is x equals 2. Our horizontal asymptote usually starts at 0. What's this -4 going to do? Down 4, so where's your horizontal going to end? Y equals -4. Now, I'm not saying you can't graph it to answer those, but I just wanted to show you, you don't necessarily have to have a graph to give me those asymptotes. You could think about, okay, I know it's at 0, so if I move up or down, where is it going to end up? All right, so let's actually draw this now and verify that. You said that this would take it right to, and that would go down 4. This time, my parent function is the 1 over x squared. So again, if you just want to give me a couple points on it, that's fine. 1 over 1 squared is 1. And we know that section is going to look like this. 1 over negative 1 squared is also 1. So that's my parent. So we had a vertical asymptote at 2. When we go right 2, it's now right there, which is what was said. When I moved down 4, I had an asymptote at 0. It will now be at negative. So now we only plotted 2 exact points, so just move each of those right 2, down 4, and then sketching the curve.
So we don't have to have 1 point.
Yeah, I'm kind of lenient on these. If you can do the positive 1 and negative 1 and then just sketch in the rest, that's fine. So we listed our asymptotes already. What's the domain of this? Negative infinity to 2. 2 was our asymptote. Our range, we're starting at negative 4, but we don't ever hit it and going up, so it's negative 4. Is that okay? Last example, I just want to show you a picture of a graph and see if we can answer some questions from it. Let's draw in our asymptotes. Where's your vertical on that? 2. And the horizontal one is at? So our domain, going from left to right, we're hitting from negative infinity until 2, union 2, goodness. Range, our y's, this is going down forever, so negative infinity to 1. Intercepts. X-intercept, that means where does this graph touch the x-axis? Y-intercept, where does this graph touch the y-axis? Half. Horizontal asymptotes, how do we write the equation of a horizontal? Y. Horizontal is y. What's my horizontal? Y equals, switch the order around here this time. 1. Vertical is x equals, so that's x equals 2. Okay. Oblique, we haven't seen any today. We will get to those. And oblique is any other line. So not horizontal or vertical, just y equals mx plus b. This graph doesn't have any other lines that we are approaching. There are none in this case. We will work more on those later. We haven't really done any yet. Are there questions? So there is a 10-question Math Excel assignment that has been opened. Remember, the one from yesterday is open until the end of the day today, and this one is open until 3 o'clock tomorrow. So that gives you time if you need to come ask any